All right, here I've described another region. I want to do the same thing we did in the last video, which is to set up but not evaluate an iterated triple integral or integrals to find the volume of this region. So it's inside of the cylinder, x squared plus y squared equals 4, but below the sphere of radius 5. So essentially, oh, and I should have added above the xy plane. I thought that, I just didn't write it. Okay. So basically what we have is we're going to have this cylinder, but instead of capping it with a plane, we're going to have a sphere, a portion of a sphere for the top part of things. Okay. So again, I'm going to set this up in rectangular coordinates first, then in cylindrical coordinates, and then in spherical coordinates. So if I'm setting this up in rectangular coordinates, I'm going to go from bottom to top. The bottom value is on the xy plane, so that's when z is equal to 0. The top is the z value of that sphere. Now if it was the sphere of radius 5, it would have been x squared plus y squared plus z squared equals 25. So z would be the positive square root, because we're above the xy plane, of 25 minus x squared minus y squared. That describes this portion of the plane. So there's my dz. Now, if I project this onto the xy plane, it's pretty straightforward because I can see that's the projection onto the xy plane, because it's got to be inside of this cylinder. So the projection onto the xy plane is just this disk of radius 2. So this point would be negative 2, 0. This point would be 2, 0. If I set it up to slice things this way, I know that's x squared plus y squared equals 4, so y is plus or minus the square root of 4 minus x squared. So I'll set it up so that my y values go from negative root 4 minus x squared to positive root 4 minus x squared, so that's my dy. And then the slices start at negative 2 and end at 2, and that's going to be my dx. Okay, now if I were actually evaluating this, I might also take a shortcut, which is to say that there's some symmetry here. So rather than going from the bottom to the top, I could go from 0 to the top and then just double it. That makes it a little nicer, because then I don't have to deal with negative root 4 minus x squared as a limit of integration. Okay. So totally fine to set it up that way, totally fine not to. All right, again, if I want to set this up now in terms of cylindrical coordinates, I've already done a lot of the work, because I figured out the bottom and the top, and I figured out what d is, which is just this disk of radius 2. Okay. So in cylindrical coordinates, I want to remember that I'm going to get an extra factor of r that's part of that dv. We're going from 0 to the top part of the sphere, which just becomes root 25 minus r squared. We're integrating over this disk where r varies from 0 to 2 as theta varies from 0 to 2 pi. So that would be r dz dr d theta. Okay, so I definitely like this better in cylindrical coordinates than I do in rectangular coordinates. Let's take a look at what we get in spherical coordinates. So here's my constant theta half plane, and here's what I see here, where this would be the sphere, this would be the cylinder. Okay. I'm going to go ahead and write in that I know I'm going to be integrating rho squared sine phi, and I'm just always going to set it up d rho, d phi, d theta. There's no rule that you have to, but in general, it's much easier to have lengths that are functions of angles than angles that are functions of lengths. So I'm just always going to do it this way. Okay, so I do know that my theta is going from 0 to 2 pi, because I saw that in cylindrical coordinates, and I can see we've got that rotational symmetry, and we're talking about the whole thing here. Okay. If I look at my constant phi rays, something interesting happens, and that's that the upper limit of integration changes. For smaller values of phi, I'm in the region if we go from 0 to the rho value on the sphere, which is pretty straightforward because it was the sphere of radius 5, so that would be 5. But for bigger values of phi, we're going from 0 to the rho value on the cylinder. So I don't have a consistent upper limit of integration. I'm going to have to break this up into two integrals. Now for both, theta is still going to go from 0 to 2 pi, because this portion, I get what I would have if it were rotated all the way around, and this portion gets rotated all the way around. Okay. But my limits of integration are going to change for rho. So what I'm going to need to do is figure out, I'm able to see that rho goes from 0 to 5 initially. That would be as phi goes from 0 to, let me get another color here. We'll call that phi equals phi naught. The phi value that passes through the point where the sphere meets the cylinder is where we're going to change. So we're going to go from 0 to phi naught, and then down here we'll pick up at phi naught, and it looks like then we go all the way down till we hit the xy plane, which I know is when phi is equal to pi over 2. So I'm going to have to figure out what that phi value is where we change, and then I'm also going to have to figure out what is the rho value on this cylinder. Okay. So, let's see, we have several tasks. Let's start by finding that phi naught. Okay. So if I want to find that, I'm going to look at this picture here and see that I have this lovely picture. Okay. If here's phi naught, I know that this point is on both the cylinder and the sphere. Now, if it's on the sphere, this is a radius of the sphere, so this is 5. Okay. I also know this distance because that distance is the radius of the cylinder. And this was the cylinder of radius 2. So I'm able to now see that sine of phi naught is 2/5. Now I can see phi naught is an acute angle, so it's in the range of arc sine. So I can say phi naught is arc sine of 2/5. So here we're going to go until we hit arc sine of 2/5, and here we're going to pick up at arc sine of 2/5. Okay, so this first integral we've got our limits of integration for rho, for phi, and for theta. Here we're just missing our upper limit of integration for rho. So that's going to be this rho value here. Let's take a look at the picture that we get for that. So here's going to be my phi. Now that's varying. We're looking at all phi's between arc sine of 2/5 and pi over 2 and trying to get this length rho as a function of phi. Okay. What do I know? That's what I want to solve for. What I do know is that this side is 2, because that is just the radius of that cylinder. Now notice the way I drew the triangle. I didn't draw it down here simply because that's where phi was. Phi was the angle that I had with the positive z-axis. Now, if I wanted to, I could work with this triangle. If that angle is phi, so is that. but I chose to just draw the triangle that already had phi in it. Okay. So now I can see that sine of phi is going to equal 2 over rho. So if I solve for rho, rho would equal 2 over sine phi. And it's okay that I'm dividing by sine phi, because sine of phi is only 0 if phi is 0 or pi. We're nowhere near 0 or pi because we're in between arc sine of 2/5 and pi over 2. So I know that that's not 0, so we're okay with that. And I could simplify that to be 2 cosecant of phi if I wanted to. So here we'll go to 2 cosecant of phi. I don't think I like the spherical coordinates for this one. The cylindrical coordinates were kind of nice because that was just one integral. Okay, and the limits of integration weren't too atrocious. Here I've actually got to break it up into 2 parts because the upper limit of integration for rho actually changes partway through. Okay, there we go.